All right, so in those last couple of kind of cheesy little riddles of trying to cross various rivers and all of those kind of things, we had a whole bunch of states and we transitioned between them in a somewhat deterministic fashion. We knew exactly what was going to happen if we invoked some type of movement. We're going to go from this number of cannibals to this number of cannibals. It was exactly set. There was no kind of question as to what's actually happening there. It was all nice and tidy. It was kind of this perfect little machine that did exactly what it's supposed to. The natural transition that we can do, and this is going to be something we're going to chat a little bit more later in the course, is that we can add in a little bit of uncertainty as how we move from, state to state. We can have some aspect of, well, normally you would do this, but there is this slight little chance that maybe something else would happen. So thinking about if you're going to try to train something to, normally it's going to do this, but I don't know, we'll allow it to maybe sometimes do this. Add some type of randomization. So if you're thinking about kind of designing some type of video game engine, you're trying to identify some type of monster movement, you want to give it some kind of set path, but you want to allow it to do something else as well. You want it to not be specifically identified, right? These are all these kind of boring video games of the 90s where you would go and you knew exactly the path the monster was going to take because it goes here. If it identifies this, it's then going to do this. And then if it sees that, it's going to do this. So you get this very specific path that's going to happen. Naturally, we want to think about adding in some type of variability. So what's going to happen is we get these same type of cute little, state diagrams. So movement between different types of states, but we can allow the movement to be a little bit more random. So we're going to have some probabilities embedded into it. So what's going to happen here is that we're going to be, at some point in time, introducing this notion of a Markov chain. This idea that we have these state diagrams that have movement, but now those little arcs are then going to have probabilities of whether or not I go down a specific path. So it's kind of the analog to these kind of finite state machines and these finite autonoma is that we're going to allow this randomization to kind of be layered on top of it. So this is something for later, is that we kind of really understand how the early kind of deterministic ones work, and then we're going to, at some point in time, add on this layer of randomization. So one of the kind of cheesy, kind of get your kind of brains attuned to this world is, one of my favorite little presentations of a problem, which is called the Drunkard's Walk. So the idea here is that we have some person who, is randomly going to be plopped in some corner. So let's say it was in some cab and he got kicked out of the cab and now he's going to stumble around a little bit. So there are going to be 5 total states, one of which is going to be his house and one of which is going to be a bar. And those become kind of the end caps. So what happens is that if this person ends up either at home or at the bar, they stay there. They're kind of like, they get home and they're like, oh man, here's my bed. I'm going to call it a night. I'm not coming back out. I don't care. If you call me 20 times, I'm not leaving my house. I'm stuck here. Likewise, if the drunkard ends up at the bar, it's going to be like, woo, I'm in the bar. I'm not leaving this bar for anything. You try to kick me out, I'm staying here the entire time. But what ends up happening is that all the other states in the middle are then going to have some amount of fluidity, is that this drunkard can move either left or right. So you can kind of think about this as blocks, and we're going to go from block A to block B to block C to bar, or all the way back to your house. So what's going to happen is that basically the drunkard has a quarter, whatever he's got in his pocket, and he's going to stand at a corner and he's going to flip a coin, and if it comes up heads, he's going to move closer to the bar. And if it comes up tails, he's going to move closer to his home. So if he were to start, let's say here at position 3, if he flips a coin and it comes up heads, he's going to go into the bar and he's stuck there. He wants to be stuck there, let's say. He's not coming out for anything. Whereas if he flips a tails, he's going to move backwards and now he's going to sit at stage 2, or at state 2, I should say. He could still technically end up at the bar because he has to flip a coin again. So if he flipped a heads, he'd come back here and he's at his kind of initial state again. He could technically get in this kind of weird little loop and he just goes heads, tails, heads, tails, heads, tails, heads, tails. Or he could, let's say, have one that it goes tails and then it goes heads and then it goes heads and he ends up back in the bar. He could have, tails, 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 and he ends up back at home. There's a whole bunch of movement that's going to happen here. So there are a bunch of kind of natural questions that end up happening. So you can kind of see the simulation that can transpire is that you randomly plop somebody in position 3, you let 10,000 versions of that person go there, and you kind of see what's going to happen as you let this whole thing kind of explode. Where does that person tend to end up? Do they end up in the bar? Do they end up at home? Do they get stuck in some little loop in the middle? How long does it take for them to go to the bar? How long does it take for them to go to home? There's all of these kind of cute little nuances that are then going to be living in the shadows about the overall movement of this particular drunkard. So you can think, like I said, what is the probability that you'll eventually reach some type of absorbing state? Is this person ever going to end up at home or a bar? Well, I mean, in the very unfortunate circumstance that you're just caught in some type of infinite loop here, then you're not going to end up in any of those. But if you're thinking about this as an honest to goodness coin flip, you're probably at some point in time going to get a run of, 2 or 3 heads, which means you're going to get sucked into the bar. Maybe you end up with 2 or 3 tails, which means you get sucked back into your home. So if you let this process go on indefinitely, at some point in time, you're probably going to end up somewhere. So then the question becomes, okay, if you start at a specific state, where are you going to end up? You're going to end up more likely in the bar, you're going to end up more likely in the home. And hopefully you can see that probably depends on where you start. If you start really close to the bar, you're probably more likely to end up at the bar. If you start really close to your home, you're probably more likely to end up back at home. And if you're in the middle, maybe it's a 50-50 split. Which actually is exactly what ends up happening in this problem, is that if you start at stage 2 or at state 2, you get an exactly 50-50 split of ending up at home or ending up at the bar. If you're on either of those little end caps, so if you started at, that's just a disaster. If you start at stage 3, you can see that there's a 50% chance right away that you're going to go to the bar. But there's also a 50% chance that you're going to end up in the middle. And then you kind of have to claw your way back out to get towards the bar. So what ends up happening here is that you have a 75% chance of going to the bar and a 25% chance of going to your home. Same thing happens if you start at stage 1, in that you're closer to home, so you have a 75% chance of going home and a 25% chance of going to the bar. And then there's a bunch of other random questions that come into play too, is that, on average, you're probably going to get absorbed into one of these locations in like 3 or 4 moves. So there's all these kind of cute little things that come into play. So there's something that we're going to see a little bit later, is this idea that we're going to dump into a whole bunch of these little transition diagrams and kind of see what's going to happen. And then it naturally leads to that kind of what happens if I allow some amount of randomization. Where is it going to go afterwards? What's going to happen in that whole process? And that's where things get really interesting when we start talking about AI and stuff like that, is that that's very naturally this idea that we have computation, and then we're going to add on a little bit of randomization. We're going to let this kind of system go. I've trained it to a certain amount, but now we're going to kind of let it loose and let it do its thing with some amount of probabilities and things like that. So that's kind of this natural process that we start with computation and then we add things to it afterwards.